Hey folks, can you hear us?
Yes, Joao, can you?
Okay. Hold on, please.
Let's try. How about now?
Can you hear João Vitor in the room?
Yep.
Yeah.
All right, sweet.
Cool. All right. So I think we can get started. Okay, folks, thanks for your patience. We had some technical difficulties, but here we are. All right. So today I'm going to present to you from text to knowledge graph using large language models. This idea comes from one of the some of the initiatives we're having in the group, which is trying to use large language models to do healthcare interventions or to support healthcare interventions. And this is a personal interest of mine as well. All right, so I think we shared the link for one of the sources that inspired this presentation, but here are other inspirations that you guys can check out. So these Medium posts and also this GitHub repository where we have the code that was developed by the original author. But essentially, let's get some concepts ready before we start. So what is a knowledge graph? So a knowledge graph, you can see here in the right, this figure, which is a very simple representation of a knowledge graph. And if we would try to define it in a few words, it's a structured representation of information where nodes are the circles where we have the names of the entities. The nodes denote entities or concepts, and edges represent relationships between them. Essentially, the knowledge graph is a way for us to represent data in a structured format. And if we would try to make it even more simple, it is organized in a series of triples. Essentially, we have the first node that is connected to the second node through an edge. Similar to what you see here in the figure, so like Mary eats lamb. And in this form of representation, we actually kind of use human language to enrich or to organize this data. And if we would go to transform an information, which is Mary ate lamb, we're going to have the first node is Mary, the second node is lamb, and they are connected with this arrow or this edge that is eats. So essentially, we are transforming, connecting two entities or two concepts with a verb, with the representation of them through an edge. And with this, we can create very complicated, I want to say complicated, but complex representations of data. So for instance, Mary eats lamb, lamb is food, a plate contains food, lamb is served on plate. This is kind of abstract, like why would we do this? But the answer is this helps the machines, the computers, to understand the meaning of data, while if we would have a table, we would not be able to showcase that much information. I'm going to go into some more examples later, but please feel free to stop me if you have questions. Well, can I just use a table for that, right? Can I just use a CSV, an Excel table to represent my data? Do I need a knowledge graph, right? This example here is something that we would see in many of the data sets that we use at Gemini and the research that we do. So essentially, we have data for a fictional patient. We have age, sex, the setting where the data was collected, the duration of symptoms, the symptoms as a binary variable, so like fever, yes or no, cough, yes or no, temperature, and oxygen saturation. So this is pretty common, right? We always have data like that. We can also have a data dictionary or a code book that describes this data. This usually works pretty well because the ones that are doing the analysis are ourselves, right? We are humans, we understand these concepts, but the machine inherently doesn't, right? This is where we have a problem. The challenge is when we are both using unstructured data or I want to say not only unstructured data, but also when the machine is trying to interpret the data. So imagine if we had a description of a case report, right, for a patient, instead of actually having a table describing this information. So I highlighted a few of these variables, a few of the data points that are going to the table here. So 42 is the age, male is the sex, ED is the setting, et cetera, but you can see how a lot of the concepts or the words are not highlighted. So a lot of this information is lost when we go for something from something that is unstructured to try to give it some structure, right? And when we lose this information, we can also lose accuracy if we're doing a model. We can lose efficiency when we're training a model, but also we lose meaning. And this meaning is something that, again, is really obvious for us that we are humans. We understand language. We have been trained in healthcare sciences for a lot of years, but the machine usually doesn't understand. If we would go into more, in a more like a clear example, if I was gonna ask you guys what is age, you're probably gonna give me a description of, well, age defines the amount of years, so the unit that a person has lived since birth. But again, we could ask ourselves what is a year? A year is a measure that every 365 or 366 days, depending on the type of the year, we have an increment of 1. So every time the Earth revolves around itself or around the sun, that is the year, blah, 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 blah. But then we are talking about humans, right? So if it's a human, an age is going to be numeric. The acceptable range is going to be in years. And usually we would say that a person would have between 0 and 120 years old. But if we were to talk about mountains, we would actually use a different type of data. We would have categorical data. We could be like Cretaceous, Jurassic era, or whatever. We would still use years. Actually, this should be units, sorry. But the acceptable range would be much larger. We would be talking about millions and millions and millions of years for a mountain compared to a human. So why do we need to understand that? Why do we need to be very clear about this? Essentially because we don't want to guess when we are doing data analysis. We don't want the computer to have to guess what is the type of data. We want to be very, very specific. And that's how a knowledge graph can be useful, because we actually enable the machine to understand and reason about data, facilitating tasks like semantic search, question answering, and recommendation systems. And we do that by creating a very, very clear data structure where we enrich the data for a single variable. We have variable name, the label, the description, the data type, units, value range, and a lot of information that we can add to the variable age in a way that the machine and also ourselves in the future, we can understand. So think of this as a next step after the data dictionary, the next step after the code book, where the information, the metadata, is actually already embedded into the information. And then we can go from things like unstructured text to a knowledge graph. And again, I apologize for this very rough figure here, which I drew myself. So I'm going to walk you guys through it.
You shouldn't apologize for not feeling sorry for it. It's nice. That was the idea, right?
Yeah, that's the idea. All of the concepts that I had highlighted before, they become notes, right? So sex here, male, we have patient ID, we have the setting, we have the fever, the symptom, the cough, etc. And we are able to link all of these informations with a verb, with a connection, like for instance, patient has fever, patient has cough. Cough is a symptom, fever is a symptom. so we can add the information to the knowledge graph. We can even go further. Once we have this network set up, we can even use the own structure of the network in the knowledge graph to start doing some quantitative analysis as well. Like, let's say we would be we could use the distance between a node and the other node, the thickness of the edges, which are the associations and all of that, to actually understand how important the associations are, right? So if you have ever seen some type of network analysis, it ties back to the knowledge graph in a similar fashion, in a way that you can use the associations and the distance, etc., to try to understand a little better. So things like node distance, edge thickness represent associations found in the data that you as a human would not be able to find looking at the table, right? If you looked at a table, you would probably, if you did like a logistic regression, you could maybe find that fever is positively correlated with age. So maybe as your age increases, the likelihood of you having a fever would increase. This is just a random example. But once you have the data and the knowledge graph set up, you can detect interactions that are usually not that obvious, because we humans were doing the analysis, and we do lose a lot of knowledge when we just try to structure things, okay? Well, before we go on, I wanted to stop and open for questions if folks want some clarification on knowledge graphs and why they are useful or where they are used before we go on. Okay, let's carry on. All right, so now we have a simple understanding, or like an initial understanding of what knowledge graphs are, how they are useful, etc. Why would we use a large language model to create a knowledge graph? Essentially, I can tell you that creating a knowledge graph from scratch is a very hard task, because you depend on things like concepts, ontologies, which are sort of abstract and take a lot of time for you to get something that works and is consistent. Using the large language models can actually help you, because they are really good at doing automated tasks, right? They are a machine. They are able to understand context, because they were trained on human language, so they can understand that if you have a sentence where, say, patient has fever, they can understand that fever is a thing, patient is another thing, and the association between them is that the patient has fever. They are really good because they were also the large language models that we know. They were trained not in a domain specific way, so they can work for math, they can work for physics, for medicine, for literature, because they were trained in a very generalistic way, right? Because they are also automated, they can be scalable. We can use them in an automated fashion and use them to train and to look at big data sets. And finally, if you already have a domain-specific knowledge graph set up, you can use the large language model to help you to transform your data to their format. So that's on its own already saves a lot of time. Of course, all of these advantages could also be disadvantages, right? You could tell me that because large language models are so generalistic, they are going to make assumptions, they're going to make associations that are not trustworthy, right? That, of course, it can be a disadvantage, and that's one thing that we would need to control for after we do the tests. In order for us to understand and try to put this into perspective, I wanted to give you guys working example from a case that we are working in one of the projects. So in one of the projects we are doing here at Duke, we are working with specifically creating personalized care plans for sickle cell disease patients, right? This is a partnership with folks at the Astro Group at the Duke Emergency Medicine Department. And essentially, we want to take the clinical guidelines that we have and try to transform them into a knowledge graph, into like a database that the machine can extract information from, okay? So here in this example, I'm using the American Society of Hematology guidelines for sickle cell disease, specifically for acute and chronic pain. This is how the document looks like, okay? So this is one of the paragraphs, so non-opioid pharmacological therapies for sickle cell disease pain. And we have a set of recommendations based on literature or expert opinion, what should be used, what treatment should be given for patients in these conditions. What pharmacological therapies that are non-opioids, right? So we have like a summary of the recommendation, we have remarks, we have citations, we have links, we have a bunch of information that is not shown here, but it's linked, right? We have symbols, we have citations from publications, and this is a very long document, right? This is a 46-page long document that it would be very hard for us to transform this to a table, right? And essentially, if we want to create a machine that is able to understand this document, the machine needs to be able to query this document, needs to find information in this document like we humans do. Like if I wanted to find what are possible pharmacological therapies, I would hit Control F or Command F in my PDF, and I would type pharmacological therapies, and I will try to browse the document, searching for those. But the way the document is right now, it is really hard for the machine to do so in a way that is reliable. And essentially, the way to do this is that we take documents. So this could be a PDF, this could be a Word document, a CSV, etc. And this could come from your, if you would do this in a different scenario, it could come from WHO, it could come from Duke, from the American Association of Hematology, et cetera, et cetera. We break down these documents into smaller chunks. So let's say every 100 words becomes a smaller document. And then we extract the meaning from these words using the large language model. And to do so, imagine if you are going to ChatGPT, right? You type ChatGPT online. We always use it. We use many different solutions as well. You would go into ChatGPT and you would ask ChatGPT to do it. You are a knowledge graph builder. Extract triples from the context text. Each triple must include chunk ID, node for nouns and entities, and edge that describe the relationship. Avoid using verbs like publish, develop, etc. Focus on nouns and concepts and output in a format that I want specifically. To give you an example, I would send this message to the large language model. The large language model would process a phrase like this. So the World Health Organization released updated malaria guidelines in 2021, and the result would be something like this. The node 1, the entity is the WHO, so World Health Organization. The node 2 is malaria guidelines, and the connection between them is released. So see how the machine processed the phrase and organized in a way that I can then build my knowledge graph. So if I would search if I would ask my database in the future, who published the malaria guidelines in 2021, the machine would be able to understand that the actual response would be World Health Organization because they are connected, right? The information is connected, and then we would be able to find out and respond to the questions. This is the output. I'm not showing you all the process, but this is the big output. So this here in the left is the zoomed out connection. So each one of these circles, if you remember, is an entity. So it could be sickle cell disease, it could be, I don't know, an opioid drug, could be a person, could be a lot of different concepts in the document, and they are connected among themselves, or actually the connection in between two, right? So they are connected in a way that we have a description of their relationship. If we zoom in the figure here on the right, you can see how there are different colors and they form communities, because some terms are connected more frequently throughout the document than others, right? So maybe this very central node that has a lot of connections, maybe this one is a concept that is very common in our document. So in that way, whenever I search for this concept, all of the connected concepts are going to be pulled together at once. So then you can actually trace back and find out why you got that answer back, okay? To put it in more practical understanding, this table here shows the top 5 communities according to the number of connections formed. So for this number of, this community number here is just random. But you have the number of nodes, the number of entities of that community, and the number of edges, which is the number of connections formed. So you can see that the first one has 100 connections. So it's a very central information. If we look here at this third community here, the third line, we can see how terms that are that are common in this community are pain management, massage, yoga, virtual reality, guided audiovisual relaxation, etc., etc., etc. So my understanding is that this community is probably linked to non-pharmacological options to treat sickle cell disease pain, right? So essentially, if I would pose a question to this data set saying, how can I treat acute pain for sickle cell disease patients without drugs? Probably what would happen is that this community would be highlighted and the information would be pulled from this specific connection, this community. So then I know that my database works because it's doing what it's intended to do. If we would go and highlight some of these communities, we would get something like this. So we have a community in orange, one in blue, and then one in green. I am not labeling them here because it's just like a big picture example. But essentially, the idea is that these points, these concepts are their connection is more intense, I would say, than the other connections. And for instance, the third community here is the green one that I was showing you. And whenever we would ask a question or try to query the data for non-pharmacological options, we would be drawing information from here. Okay? Questions? No? All right. In summary, why is this cool? Why do we need to do this? Why should we actually build knowledge graphs out of our data sets? If you would go to ChatGPT here in the figure in the right and type, what are non-opioid options to treat sickle cell disease acute pain? You would get an answer, right? You always get an answer, regardless if it's right or wrong. So it's listing here for me non-steroidal anti-inflammatory drugs, paracetamol, adjuvant medications, and the list goes on and on. But I could ask and we could discuss, where does this information come from? Can we trust that this information is safe and is accurate and can be used to actually treat a patient that is in pain? We don't know. Well, we assume that this information is correct, right? Because, I mean, it's giving you an answer, we probably can trust it, right? Well, we are talking about a patient giving care to a real patient, to a real person that is in pain. So there's this issue of, can we actually trace back to a actual source, like a PDF of a published article, a PDF of the American Association for Hematology or whatever? And then the other question is this being generated, or is this being actually retrieved? The difference here in the concept that I want to highlight is that what ChatGPT does, it doesn't recall from actual memory, it generates information. So for every response, it is actually making up information. For every single word, it's like it's imagining the response, not actually recalling from a true fact most times. And that's how the standard way of doing using the large language models can be problematic when you are dealing with risky situations, like for instance, for providing care for patients. But the solution is that when we build our knowledge graphs, we can actually leverage the structure to query and actually extract information. We are not imagining the response. We are actually going to the document, getting the information from the document that is in the knowledge graph, and actually generating the response. So I did the same exercise. I asked, what are non-opioid therapeutic options? And I got this response. Non-opioid pharmacological therapies for acute pain include blah, 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 blah. The cool thing is that if I went to my document and I searched this exact phrase, I would find this exact phrase in my PDF. So we are making sure that the response we are getting, or at least that the output that we are getting is tied to the PDF. And we can actually trace this. This example output here shows tags where we can actually find. So the page where this information was extracted from is page 30. It starts on the word 785. The creator was such, the producer was such, the date was such, in a way that we can trace this back to the original source. So then we can ensure that the response is going to be reliable, that it's going to be traceable, and it's going to be grounded in actual data. I'm not, and the thing is, we then can combine different sources from the document to generate a better response that we actually want. So I'm showing you just one of the hits, I would say. When I prompt the model and then ask this question, I got 5 hits from the database. And these 5 hits were from separate sections in document that combined generated this response. Okay, so the model is getting, imagine that you are writing your introduction. When you're writing your introduction for your paper, you read a bunch of publications, and based on the knowledge that you got from these publications, you actually use that knowledge to build your own paragraph. So that's what we are trying to reproduce here. We are taking actual information and using the actual information to generate a reliable response. And finally, the other aspect of why this is cool is that we are using local open source models, okay? What I mean by local, when you go to your browser and you type ChatGPT, you are using a company solution that runs on their cloud. So everything that you type can actually be stored and seen by the company, okay? But when we are working with patient data, when we are working with sensitive data, we actually want to be mindful that the data is not leaked, right? So if you are using data from the Duke EHR, if you are using data that comes from KCMC, one of the projects that we have like with the registries. We don't want this data to be stolen or made available online. So when we use local models, we take one of these big machines, the large language models, and we run them in a protected environment. In this case, I did it in my own computer, in my own laptop. And the other really cool thing is that I used an open source model. So this model, differently from ChatGPT, is something that was built and released online for people to use them for free. And this would be really, really cool because we can then leverage this for places where there is resource limitations, funding limitations, and we can then build on top of the model. So let's say this company here, the model called Llama was built actually by Facebook and was made open source. We can download their model and then use it to build our version of it, to build a better version of Llama that is suited for maybe to be used in Swahili, because maybe the model was not trained in Swahili, so the interpretation of Swahili language is not as good as it is in English, right? And essentially, we can then repurpose this to do a lot of different research, a lot of different outputs and projects. And I'm listing here just a few options that if you guys want to try it out. The one that I used is Ollama, this version here. But we have LM Studio, we have Hugging Face, we have Gem, which are all options for you to download the large language model on your machine and try to use it and do the tests. All right. This is what I had today. Thank you all for listening. And if you have any questions or if you want to go back to any topic, please let me know.
Thank you, Joao.
Thank you very much. No, oh, sorry. Okay. Yeah, I was just about asking before you.
Hang on,
Vale, hang on.
hang on.
Okay.
Sim. Isso, agora aumentou no mim.
Okay, try again.
Can you hear me now?
Yes.
Okay, cool. Yeah, I was just about asking, I mean, when I saw the knowledge graph, right, there's so many nodes and is it edges?
Edges, yes.
Yes.
Yeah, nodes and edges. So I was like, man, but this is too robust. How do I make sense out of this? I was just about asking the question before you put the next slide that kind of said, why is this cool? And it's indeed cool, as I can see, because it seems it's not much about the knowledge graph itself, but it's more about what you can get from it.
Right.
Yeah.
Right.
Okay.
You could basically go the two ways about it. If you want to focus on the actual structure of the knowledge graph, you could actually refine and make sure that it's working really well. But that in the end, what I wanted to achieve is actually to be able to do the queries and get the actual results out of it. If you go to some of this is related to some of the grid work we were doing, right? With all of those data definitions, that the common data models that we were talking about, they are ontologies, they are knowledge graphs, I want to say, structures that are defined and pre-existing for a few areas. So if you go to genetics, if you go to omics overall, there are very clear and defined structures, but for some fields, this is not the case, right? There are situations where you don't have that pre-existing structure. And for my example here, what I wanted to do specifically was to work on a document that didn't have structure before. So that's how it was useful in my case. But I can tell you that I'm only showing you the part that worked, but there is a lot of it that didn't work the way that I intended to. So there's a lot of refinement to be done to make sure that I'm getting a meaningful knowledge graph.
So there's two pieces to this presentation that I want to make sure you all understand. One piece is knowledge graphs, what they mean and what they're used for. The other piece is how you can use knowledge graphs to further refine how you can access information from using LLMs, or even to use LLMs to help build the knowledge graph, which is kind of like a iterative process. Now, what Joao is trying to illustrate is that if you get a body of information, in his example, all the clinical practice guidelines for sickle cell disease treatment, and then you structure them into a knowledge graph instead of being documents that the LLM has to review every time you ask for a question, then you will facilitate the architecture of building a solution that uses LLM prompts to extract information from a different source and provide you with input, which is basically making inference. So if I want to make inference using large language models, and I want to make that inference sourced by different documentation, this is transforming that documentation into a knowledge graph is a step in the process that will likely facilitate the integration of data the LLM will learn from. Does that make sense? Okay.
A lot of sense.
Okay. So the other piece that João Victor was presenting was that you can use the LLM to derive the knowledge graph. So the LLM will also will help you derive the knowledge graph, which you can also do with other types of approaches. You can do it on the source of code. There's several packages in different programs that will derive a knowledge graph out of a piece of body of unstructured text or structured text. The LLM will have this added layer of inference to it that might make the process easier. I'm not sure if you were able to find comparisons of building knowledge graphs manually or building knowledge graphs through some sort of automated Python code. I don't know the library, still refer to a particular library, but compared to the LLM, if there's any added advantage to it, besides the easiness of the work, of course.
Yeah, the libraries that would go about it are usually based on natural language processing overall. So there are already some AI to it to build it, especially when you are working in a field that doesn't have a lot of background. And the caveat I would say is also that using the large language model to do it is also takes some time to do it. It's not really like automatic.
Right. Sure, of course.
So for instance, for this one that I built, it took me, I want to say 4 to 5 hours for it to run and get the results in my machine. Of course, if you had like a big server, it would take less time. But that's one of the caveats as well. I guess you pay a little because of the flexibility of it.
Yeah, I would be curious to see what is the added performance, time, and number of inputs needed to extract the same information if you have stored the document as a knowledge graph prior, or if you store the document some other way as you...
Yeah, the other way they usually would go about is like using the vector stars,
right,
which have some benefits and some...
Yeah, and from a very lay perspective, I'm just thinking, when I upload a PDF on ChatGPT and ask it to extract meaning from it, I wonder if it's not doing this process in the background, or if it's just trying to search through the document.
Yeah, that's a good question. Because
that's what I would expect.
Since the response is so quick, and I would anticipate that it's running some Python code behind to make it to process it overall. Yeah.
So I want you to understand the intuition of this, because we're gonna play with this more and more. Now, the other part of this, Obali, that maybe it's another aspect of this presentation is taking away the part of the LLM, just looking at the knowledge graph. I want you all to understand that a knowledge graph is a different way to represent data. And I think João Victor was very clear on that part of the presentation, that different from keeping data as a table, and he showed the CSV versus the knowledge graph information, or keeping the table in some sort of relational database where you transform the data into the concept of a semantic data. There are different ways to store data, and the different ways you store data, or let me say not store, the different ways you represent data will allow you to do different things with the data, or will facilitate the process. So the example João Victor gave, which is why I think knowledge graphs are a very useful tool to represent data, is that when you represent data in tabular format, all the relationships between the different variables, by the definition of the variables, but also by the interaction between them, are stored outside of the data itself. So it's not something that if I throw a CSV into a computer, that the computer, the program, ChatGPT, or whatever, will automatically comprehend the connection between this.
Yeah.
And so now imagine that I'm trying to combine different data sources that are all linked by a particular set of variables. So I have two data sources. One, they are linked by patient ID, or then I have another tabular data that now is linked to my data based on municipality, or I find some different linkage variables between data sets that are at different levels. If you don't embed in the data representation how these different pieces of information are tied together, those data will never be able to be linked. Yeah. Unless you have the person who created the data, or you have an extensive documentation that will allow you to make that connection. Now, representing that into some sort of knowledge representation, like a knowledge graph, would allow you to embed this reasoning, embed the meaning between the relationship of different pieces of information in the whole data representation, which is why I think it's very unique and beneficial tool. Now, I want to say that understanding that there's a lot of knowledge to gain in that space still, and I think that's none of our expertises. So hopefully going to be bringing in more examples or more people to talk about this as we develop it further.
Yeah, and as a like a personal example of how this could be beneficial, like we're trying to get data from the electronic medical records here at Duke, and even using some of the tools that are they're actually made to not they're known code solutions. Like you can search, you can click, and you can use like a nice looking program to do it. When you actually want to get in and get the real data out, you need to know code to do it, and you need to know what the variable names are, right? So let's say you want to search for patients that are between 30 and 60 years old that had asthma in the last 20 weeks, whatever. You need to know the variable names, and that's always a problem. Yeah, that's always something that is an issue. You need to know how to code. The understanding here that we can also get eventually is that once you have the knowledge graph structured, you could use language, because human words, like I want patients that are between 20 and 30 years that had asthma, and the model is going to understand that this language means that variable means that patient. And eventually you can get much more easy access to data than you had before. And not only it's easier to query data, but it's going to be easier for you to get the information and model and get better results at the end. So that's our ultimate goal, I would say, to enrich everything. Yeah.
Cool. All right. Thank you, João Victor. Any other questions or comments? All right, great. So as we discussed last week, we're gonna take probably the next meeting. I'm gonna ask Gabi to excuse us and push her presentation a little later to get us back on track with our template season, and use the meeting next week to reorganize, see where we're at, redistribute, for us to get going with our seasonal event. All right, great. So we'll check in again next week. Thanks everybody for joining. Hope it was enlightful for some of you as it was for me.